Hi everyone, welcome to the last video of this week, and in this part we will be looking on how to quantify the uncertainty about our estimates obtained through the EM algorithm, and we will do that through the bootstrap, which was originally proposed by Bradley Efron in 79. And remember that when we use the Newton Raphson or the Fisher scoring to maximize the observed data likelihood as a byproduct, we not only obtain the maximum likelihood estimates, but we also had the observed Fisher information available. And we have been applying the EM algorithm to a variety of problems, but the EM algorithm only provides us with point estimates. There is no uncertainty quantification in the algorithm. And although there are analytical methods that allow us to quantify the uncertainty about our EM estimates, for instance, the method proposed by Thomas Lowes in 1982, we will not cover such methods, but we will instead look at a more general method for uncertainty quantification that can be applied in this setup as well, and it is the bootstrap. And as I said, it was proposed by Efron in 1979. And basically, the essential concept of bootstrap is to emulate repetition of the experiment by simulating new data on our computer. Ideally, we would go out there and collect new data sets. Then, for each new collected data set, we will apply our procedure, in this case, our EM algorithm, and we will obtain a new estimate. And at the end, we would have a collection of estimates, and we could approximate the variance of our original estimate by calculating the variance across the estimates of the data sets that I have collected. But of course, collecting new data sets and potentially many data sets, but even if it's just one, it's infeasible by several reasons. Sometimes um, we don't have the time to do that, and even if we have the time, collecting data as associated costs. So we basically in practice can never collect new data just for the sake of obtaining the variability of our estimates. And so what the bootstrap proposes, okay, I cannot collect new data, but assuming that the original sample, the original data that I have and that I have used to compute my estimate, I can simulate new data from this data, and provided that my original data is representative of my population, it's okay to do that. And so I simulate from my observed data new data, and we will look on how to that in 1 minute. And basically the bootstrap, by it's a resampling, because we are resample our original data, or simulating new data from our original data set. And basically it eliminates the need for the mathematical theory. For instance, those who have done statistical theory, you have look at procedures like the delta method to approximate the variance of the estimator. So the bootstrap, in one way, it eliminates the need for mathematical derivations, but of course it does not eliminate the need for thinking about the problem that we have in our hands, and how to how to properly come up with a bootstrap scheme. But okay, without further ado, and the bootstrap, as I said, is a general method for obtaining variance of the estimators or to compute confidence intervals. And basically, what we do is that we generate artificial data and call it, we have our estimate based on the original data, call it theta at, and we want to quantify uncertainty, to quantify our uncertainty about this estimate theta at. And the bootstrap does that by emulating the process of data generation and model fitting, and we generate artificial data, say YB, where B stands for bootstrap sample, and from we basically generate artificial data, say YB, from a distribution that approximates the true unknown sampling distribution of the actual data. So we generate data from a sampling distribution, and this sampling distribution approximates the sampling distribution of the original data, and we use this to generate an artificial data set, and then for this artificial data set we compute again our estimate, and we do this many times, say b times, and at the end what we have is a collection of estimates, call it theta at b, where B stands for the bootstrap dataset, and we have many of them, many bootstrap datasets that were artificially generated. And one way to do this is the non-parametric bootstrap. And in the non-parametric bootstrap, we are approximating the sampling distribution by the empirical cumulative distribution function, as the name non-parametric bootstrap, because the empirical cumulative distribution function is a non-parametric estimate of our um, of the of a distribution function. And we have here its expression. We should all be used to this, but more than that, generating data from the empirical CDF, it's equivalent. The empirical CDF basically puts weight one if our original data has sample size of n. The empirical CDF places weight at weight of 1 over n at each data point, okay? And basically this is equivalent resampling from the or generating data from our using our original data set, and then using the empirical CDF to approximate the sampling distribution of our estimate. This is equivalent as resampling from our original data. So we have our original data and we just resample from our original data, and we do that, we resample with replacement, right? Because imagine that I have 5 data points and I need that my bootstrap data sets, they have the same size as the original data. So if my original data, if I have 5 data points, my first bootstrap data set, it needs also to contain 5 data points. So if I go to my original data set, if I sample one observation, I put it on the bootstrap dataset, and then if I don't put it back, because my bootstrap dataset has the same needs to have the same size as original data, so I end up with the same dataset. And of course there's nothing wrong with that. I can compute again my estimate, but then I will obtain the same estimate that I have obtained. So in terms of uncertainty quantification, then all the estimates are the same because all of the bootstrap samples are the same. So I resample with replacement. So I pick up one observation and I put the observation back in my original dataset so it can be picked up again. Okay. And for instance, just to illustrate this, imagine that I have my data, call it, sorry, it's not writing, data, and I have that it's 1, 1, 2, 3, 4, or 5, 4. Okay, so we have 5 data points. Okay, and now I will sample a new I will use the command sample and I will resample from this data set. So So basically, what I'm saying is, sorry, it needs to be with capital. What I'm saying is that, okay, I have, this is my data set and I will resample from this data set. How many data points do I want? 5. It's the size of my original data, and replace equal to true. So once I have picked up one value, I put it back. And if I do this, that's my bootstrap sample 31312. So in this case, 4 was not picked up. And if I run it again, I obtained a new sample. Of course, this is very toy because I have very few data points, and these are my bootstrap samples. Okay. And then, for instance, imagine that I'm interested in the mean for my original data and I want to quantify the uncertainty. Of course, for the mean, we know what is the variance of the mean, but just to make my point. So I compute the mean based on my original data set, and then for each of the bootstrap datasets. In this case, I have 3. Of course, in practice, we need a lot more, but again, just to make my point. So I have these 3 datasets, and for each of these bootstrap datasets, I will compute the mean again. So at the end, I have 3 means, and I can check what is the variance across these 3 estimates, and this would be the variance that I will use to quantify the variance about my original estimate. Of course, only 3 data sets, it's nothing, but just to make the point. And that's it, the non-parametric bootstrap algorithm, and we have it described here in these 2 steps. So basically we resample, say, b capital number of times. So I generate a bootstrap sample, call it y raised to b, sorry, and by randomly sampling from my original data with replacement. And then for each bootstrap data set, I will compute my estimate, and I denote it by theta hat to the power of b, using the bootstrap sample, the b bootstrap sample. And again, I can calculate the variance of my original estimate. Theta hat is my original estimate based on my original data as the variance across the estimates that I obtained in my bootstrap procedure. And about confidence intervals, imagine that I'm also interested, and most of the times I am interested in computing 95 confidence interval, say 95% confidence interval for my parameter. And there are many, I would say thousands, but maybe I am exaggerating, but there are many ways of computing bootstrap intervals, uh, some fancier than others. We will use a simple one that works well in many situations. And what we do is, okay, at the end of my bootstrap procedure, I have b capital estimates, correct? So a confidence interval for my parameter, theta, a 95% confidence interval. I can just look at all my estimates and I can compute the 2.5 and the 97.5 quantiles of my estimates, and this will serve as a 95% bootstrap confidence interval for my parameter. And that's exactly what we have here, and this is known as the percentile method. And natural question that can arise in this situation is how many bootstrap samples or simulations do we need? And it depends on what we are interested in estimating. If we are just interested in providing a variance or standard errors, we need less bootstrap samples. But for confidence intervals, and because we are for instance, for the 95, I needed the 2.5 and the 97.5 quantiles, and these are kind of extreme. So I need a large number of bootstrap samples, and Davison and Inkley. Davison and Inkley, it's a book on bootstrap, an entire book dedicated to bootstrap methods. There are at least three books entirely dedicated to the bootstrap. Davison and Inkley is one of them, and they recommend, when we are interested in, say, 95% confidence intervals, that we should perform at least 1000 bootstrap simulations. Of course, for the examples that we are seeing, this is kind of fast, and nowadays our computers are powerful, so this is not a big problem. Of course, in 79, when the bootstrap was proposed, resampling 1000 or 2000 times even a regression model was challenging. Nowadays, depending, of course, if the procedure that we are using for our original data is very intensive, and because there are a lot or several people taking machine learning here. For instance, if I'm using like a neural network, of course, most people that use neural networks, they are not that interested in uncertainty quantification, but they should be. And if they have to resample their data and then apply the neural network, it can take a while. But for the examples that we will be looking here, it runs very fast, as you will see. So I will apply the bootstrap to two examples. I will first revisit the genetic linkage example that we have seen last week, and then I will also apply the bootstrap to the two-component Gaussian mixer model that we have seen in the first video of this week. Okay, so remember the context for the genetic linkage example. We had multinomial data, and we had four categories, and we know that the number of observations falling in each category was 125 for the first category, 18 for the second, 20 for the third, and 34 for the fourth. And then we had came up with our Q function for the E step, and that's what we have here. And then our M step was given by this updating equation for theta. Basically, we had probabilities for each of the categories, and they depended on theta, and our goal was to estimate theta. Okay, and so the first thing that I have here, it's basically the code for applying the EM algorithm to our original data. We have already done this, correct? And that's what I have here. So let me run this. And that's what we have obtained, right? So 0.63. Now I want to bootstrap in a non-parametric way. That's what we have learned, my data, and I will do that 2000 times. So I will create 2000 bootstrap samples, and then I will apply this function to each of the bootstrap samples. Okay, and basically don't forget that when we look at the data and the data is given by this means that I have four categories and that I have 125 observations in the first category. So this is equivalent this is equivalent to having 125 ones, then 18 twos, 20 threes, and 34 fours. Okay, and that's what I'm writing here, because now I will resample this. Okay, so for instance, let me just, if I do this, let me just, yes. And then for instance, how does a bootstrap sample look like? Yep. So, and because in my code I'm passing the number of ones, the number of two, the number of threes, I'm not passing the data as this. What I have done is to come up with, if I do table, if I do table of these, that's the form that I need then for the function that I have created. This is all depending on how we code things. Okay, so I see that for this bootstrap sample, I have 127 ones, 17 twos, 25 threes, and 28 fours. Okay, and I will do this 2000 times. And here, that's what I'm doing. I'm doing a loop. I'm not saving the bootstrap data. I don't have any interest on that. And what I'm saving is the estimate for each of the bootstrap samples. There are 2000 of them. I have created a vector of size big capital, where big capital is 2000. And I'm here just applying the function that we have created above to the bootstrap data set. Okay. And then I can, at the end, I have 2000 bootstrap estimates. I can compute the standard deviation or the variance across the estimates to have an idea of the variance of my estimate, or I can compute the confidence, the 95 confidence interval based on the quantiles, right? So here I have all my estimates and I'm computing I'm using the quantile function, and which quantiles? 2.5 and 97.5. And if I do this, it's fast. And that's what I have obtained. The estimate based on the original data, it needs to be contained in our interval, right? It's 0.63, and then the 95 confidence, bootstrap confidence interval for theta for the original parameter, it ranges from 52 to 0.73. And for instance, if I look at the first, say, 20 estimates, bootstrap estimates, that's what they look like. They are kind of close to the estimate that we have obtained from the original data. Okay, and that's it, as simple as it. We resample with replacement from our original data, and then we apply our original procedure to the bootstrap data set, and we do this many times. In this case was 2000, and because it's very simple, not that my code is particularly efficient, we have done that in a very fast way. And now for the mixture model, it's exactly the same thing. I haven't recorded a video about the mixture model on how to fit the mixture model in R, but we have it here. I've used the function. This is the function for my original data, and that's I will use it later for the bootstrap data. So I have called it em.mixer.to.normal. And basically, this is very similar to the other functions that I have coded for the EM algorithm. So it takes as input the data, an initial value for theta, in this case theta has 5 parameters, the weight of the components, the means and the variances, and an epsilon for the convergence criterion. And this is very similar. Basically, theta, I'm saying that then theta, uh, I'm I'll initiate it with the initial value, and theta is a vector, and I'm saying that p is the first component of theta, mu1 is the second, the standard deviation of the first component is the third component, the mean of the second component is the fourth component of theta, and the standard deviation of the second component is the fifth component. You can define it. It's up to you how you define this. And then this is very similar to what we have done before. Here I have the E step. Remember that for the E step, it doesn't compile the expressions, but this is the expressions that we had for the E step, and this is the expressions that we have derived in the first video of this week for each of the components, for the weights, for the means, and for the variances. And basically that's it. And okay, the data is it's a built-in data set, so it's a data faithful. I have attached it, and this is just for the original data. Okay, then what I have done is exactly what we have done before. I will also simulate 2000 bootstrap data sets. My estimates now, I will save them in a matrix, and basically each row corresponds, I have 5 rows corresponding to the weight, the mean of the first component, the standard deviation of the first component, the mean of the second component, and the standard deviation of the second component. And then I have B columns, okay? And B is 2000. And exactly the same thing. I'm resampling from my observed data, and then I'm applying the procedure that I've used for the original data. And then I'm computing the quantiles, and now I will look parameter by parameter. And if I do this, it was fast yesterday. Yes. So I have here this table. So I know that the weight, my P, the weight of the first component, the estimator on the original data is 0.36, and then a 95% bootstrap confidence interval for P is from zero point 0.3 to 0.42. For this is the estimated mean, and the 95% confidence interval for the mean of the first component for the true parameter is from 53 to 56. And if we remember the histogram, it's sensible. And this is for the other parameters. And that's it about the bootstrap or the non-parametric bootstrap. We resample from our original data, and then we apply our procedure, and we end up with as many estimates as bootstrap samples, and the variance across the bootstrap samples can be a good proxy for the variance of my estimate, and also the quantiles of the estimates are can be regarded as a 95% confidence interval based on the percentile method. And my goal was mainly, as I said at the beginning, there is an analytical procedure for the YAM, the Lois method. I will not cover it, it's very specialized and we don't have time for everything, but I think the bootstrap, I do not know whether you will cover the bootstrap in statistical programming or those who are undergraduate students. If you have seen the bootstrap in statistical computing, I think it's a useful procedure, not only for incomplete data as a general procedure. And we are concluding the study of the EM algorithm. The EM algorithm is a kind of family of algorithms because there are many EM type of algorithms, and of course we cannot cover all of them. It's not our goal here. And yes, I because I have a book that's it, the name is called the name of the book is the YAM algorithm and its extensions, and it's somewhere here, but it's not, I cannot see. Let me give me 1 second and I think I can find it. Yes, it's here. So basically we have this book, the EM, I don't think you can see it very well, the EM algorithm and its extension. So I mean, we have an entire book dedicated to the EM. We have just dedicated a couple of lectures to it, but at least I think it was an introduction to the topic. And starting next week, we will be starting the last topic of this course, which is multiple imputation. So see you next week. Thank you.